Welcome back to Cloud 42, I'm James. Today we're going to get started on some upgrades for my Grizzly G0602 lathe, and we're going to start with a 3-phase motor and a variable frequency drive to add variable speed capability to the lathe. This is something that I've wanted for a long time, but it's something I've been putting off, but I finally had something that made up my mind. If you've been watching the tool post grinder build videos, you've no doubt heard that sound. The good news is that is not in the spindle bearings, that is actually in the motor itself. If I disconnect all the belts and spin the motor shaft, it makes that same horrifying noise. Now, it may just be a centrifugal start capacitor switch or something in the motor, but it doesn't matter. As long as I'm going to have to be pulling the motor out of there anyway, I might as well put something back in that I want. Now, I'm hoping that this turns out a little bit different from many of the other VFD install videos that you've probably seen on YouTube. I'm hoping to actually go through this and look at every step in detail, explain the parts I chose, why I chose them, what the ratings on the motor mean, how to program the VFD, and actually how to do the install and get it set up and working from beginning to end. So let's go over to the bench and take a look at the parts. Okay, this is the motor and the VFD that I purchased for the lathe. The motor, let's take a look at the motor first, and let me show you what it is and why I selected this one. Okay, this is a Leeson electric motor. This is what's called an IEC metric motor, and that's just a particular size. This is a D80 frame, and this is the same as the motor that comes on the G0602 lathe. It's got a mounting foot on the bottom, electrical box on the top, and then the shaft on the end is keyed with a captured key and a shoulder, and it has an M6 screw in the end to capture the pulley or the gear or whatever you put on the end of the motor. So by starting with, you can start with other motors and build adapters and mounts, but by starting with a D80 metric motor, this will drop right into the lathe, and there's no mechanical work required in order to put this thing in. So let's kind of go down and look at this motor. There's the catalog number. You can look that up if you like. So this is rated for continuous duty continuous. Some motors are rated to run for some period of time with some duty cycle, so they have to be turned off to cool. This one is rated for continuous duty, which is what you'd want on a machine tool. It's rated for 3/4 of a kilowatt, which is 1 horsepower. And again, that matches what's on the lathe from the factory. Again, I think this thing is going to produce more torque because of the way it's driven with a vector drive, but we'll get into that later. The amp rating, there's 2 amp ratings here. It's 3 amps or 1.5, and that depends on what voltage you run it on. You can see the voltage down here. It's rated for 230 volts or 460 volts. What's going on is this motor has twice as many windings as would actually be required, and you can either wire them up in series so that it'll run on 460 volts, or you can wire them in parallel so that it runs on 230. And if you're running it on 230, it's going to require 3 amps. If you're running it on 460, it's going to require 1.5 amps. We're going to be running it on 230, so we're looking at 3 amps current. RPM 1740. Call this 1800 RPM with some slippage to develop torque. And so these motors come in a couple of flavors, depending. But if you're running on 60 hertz, there's basically 2 flavors. You can get them that run at 1740 or 1800 RPM, or you can get them that run near 3600 RPM. And the difference is just the number of coils in the motor, the number of magnetic poles that are in the motor. The one that runs at 3600 has essentially 2 poles. Now, there's more than that because it's a 3-phase motor, but it's essentially a 2-pole motor so that the rotor makes 1 revolution per electrical cycle. This one has twice as many. It's a 4-pole motor, so that it takes 2 electrical cycles to make 1 full revolution of the motor. Hence, we're running a little less than 1800 RPM. And that 1800 or 1700 RPM is the speed of the stock motor on this lathe. So I've got efficiency, 85%, power factor. The other thing that's here that you may or may not be familiar with is service factor. This one's rated at 1.15. And essentially what that gives you an idea of how well the motor meets its specification and how much reserve is there. So 1.15 means that this motor can run and deliver 15% more horsepower than its rating on a continuous basis. Now, that doesn't mean you want to do that, but by looking at this, you can get an idea of how long the motor's going to last and how it's going to handle overload. So it's a measure of how well the motor dissipates heat as well. So if you have a service factor of 1, it means it just meets the rating. That's closer to kind of consumer level gear. 1.15 is better than that. The motor's going to last longer, be more durable in this application. There are much higher service factors if you want to pay for a motor, pay more for the motor. You can get these as high as 1.5, and that's a motor that's rated to handle a 150% overload. But the 115 should be just fine for this application. Again, this is a home shop, and this is not going to see heavy industrial duty, and even if it did, I think this would be fine. One other thing that's down here, you'll see that this is an inverter-rated motor. So a three-phase motor is designed to just be connected to a three-phase supply where the power is sinusoidal. You have 3 phases sine wave power. And if you're going to run it on a VFD, in this case, it's rated for pulse width modulated variable frequency drive. You're actually not providing a clean sine wave, you're providing a pulse width modulated sine wave. And the maximum excursion voltages can be higher, and so you want the insulation winding of the windings in the motor to be rated for those higher spikes. And in this case, so you do want, if you're going to be running a VFD, you want an inverter rated motor, and this one is. Let's see, what else is here? Intrusion prevention code. This basically just tells you how well the motor is sealed up. And this one actually has dust and oil seals on the input and the output shaft, and the rest of the motor is entirely enclosed. So these are the specs if you're running it on 50 hertz. There's stuff moving around here. These are the specs if you're running it on 50 hertz. And then the last thing down here is the speed range. This one has 10-to-1 speed range. Now, in theory, what this means is this motor can be run at 1/10 of its rated speed of 1740 RPM. So if we're talking about 60 hertz, it means we can run this motor all the way down to 6 hertz without overheating, in theory. I mean, you know the difference between theory and practice. In theory, there's no difference. Now, I'm not going to do this. I actually don't know what the VT means. I'll have to look that up. But running this down at 10-to-1, I'm probably going to run it down that low, but since this motor is cooled using a fan that's attached to the motor shaft, if we're running it all the way down at 6 hertz, or in this case, 175 RPM, it's not going to be getting the same cooling air, but if we're using a VFD to drive it with the same torque, then it's going to be producing the same heat without the air. So I'm ultimately going to put a supplemental cooling fan on the back of the motor and rig that up with the VFD to provide airflow when the motor is running slowly. Okay, let's take a look at the VFD. Okay, this is the VFD I bought. This is a Teco-Westinghouse L510, so 1 horsepower VFD. These are commonly available. I just bought this on Amazon, but you can get them from pretty much any industrial supplier, any motor warehouse kind of place. Take a look at the tag here. See if I can get this so you can read it. Okay, this is the model on this is the L510-101H1U, and all of these, the L510 is the model of the inverter, and then the rest of the numbers and letters here actually break down essentially the information that's down here below it. So this is rated for a 1 horsepower, 0.75 kilowatt motor, which is exactly what I'm running. Now, the VFD can actually run motors that are smaller than that, but you have to dial down the current that it delivers, and there's settings to do that. So this is designed for AC input of 1 phase, 120 volts, and there's a fairly wide range it can accept, 50 to 60 hertz. Now the reason that you can run it over such a wide range and range of frequencies is that this AC input is not being used to run the motor directly. Instead, this AC input is being converted to high voltage DC, and then that DC bus is being run through some insulated gate transistors, some IGBTs, to actually commutate and create the output waveform for the motor. So again, I'm running this on normal household voltage in North America, which is 120 volts, 60 hertz. And then the inverter is going to output three-phase, 0 to 240 volts, 0 to 600 hertz at up to 4.3 amps. So what's going on here is we're actually stepping up and converting this voltage that's on the input to three-phase voltage on the output, which is, you know, what you have to do if you're going to run a high voltage, or in this case, you know, low voltage 230 volt motor off of normal 120 volt household current when you only have a single phase. Now, this is capable of 4.3 amps output, and you saw on the motor only draws 3 amps. So what's going on with the 1 horsepower and the higher current rating? There's a couple of things. One is that the current flow is a little bit different on PWM than with a normal sinusoidal waveform. But the other thing that's going on is that this is actually rated for 150% overload for 1 minute. The idea being that the VFD can provide additional current that's required to start a motor in hard starting conditions where it's got a load on it. So you can actually draw 150% rated power for up to a minute, and this VFD will handle that. Now, if you didn't have a VFD that could handle that, you just wouldn't be able to start the motor as hard. Not a big deal. And this one is actually UL listed. Surprise, surprise. Okay, so we've got the motor and we've got the VFD. I do not want to just go stuff all this stuff into the lathe and then start wiring it up for a couple reasons. One is that I don't want to discover if I have a problem and I need to use the lathe that I have to rip everything back out in order to put the old motor back in. So I'd like to know that everything is working. I'd also like to get all the programming sorted out and, you know, figure out if there's anything else that I'm going to need to buy or, you know, that I don't have on hand. I'd like the installation of the lathe to go smoothly, especially since I'm going to be taking the controls on the lathe apart to remotely control the VFD. And once all that stuff's unwired, I do not want to have to put that back. So let's start by looking at the wiring on the motor. The electrical connections on this motor are all in this box on the top. So let's start by opening that up and take a look at what we've got. Okay, this is what's referred to as a 9-wire motor. So what's happening in here is there are 9 wires that are coming up from the various coils in the motor body to these 9 terminals on the top. Now, it's a 3-phase motor. We're actually only going to connect 3 wires to this. But the reason you've got 9 wires coming up is because this is a dual voltage motor. It can either be wired to run at 230 volts or 460. And the way you do that is by shorting the wires together and connecting them in different combinations to either put the coils in series or to put them in parallel. So there's a wiring diagram. Let's see if you can see that. There's a wiring diagram here on the inside of the lid showing low voltage, which on the nameplate is 230 volts, and high voltage, which is 460. So if you have high voltage, you want U2 shorted to U5, V2 to V5, W2 to W5. And if you look, that's exactly what we have, is those 3 shorting bars are up on the top. And then the phases are connected down here. That's high voltage. We want low voltage, which means we have to connect the bottom 2 terminals in each set, which means we have to move these shorting bars down to here, and we need to connect the 3 on the top here together. Now, I don't have shorting bars for those, so once I move these down, I'll just go ahead and move all 3 of those onto the same terminal, and so they'll be connected. So that's easy. The other thing we need to do is need to connect a ground. Now, I've actually seen other videos where people are thinking that these are the ground terminals that you're supposed to use, and yes, these are ground terminals and can be used, but they're outside the box. I don't know how well you can see it, but this little shiny spot right down here inside is a ground terminal that's inside the box. It's hard to get to, but if you take out this one screw and move this block, it's easy to get a wire down onto that, and that's what we're going to do. Before I go any further, the other thing that I want to address is right now the cable entry is through this gland right here on this side of the motor, and that will be pointing straight up when the motor is on the back of the lathe. And I would instead like the cable to come in from this side. So we're going to pull this box and rotate it 90 degrees. So let's start by just pulling the box off, just to make it easier to get at everything else. And then this box just comes free, and you have to sort of wiggle it a little bit to get it off. And there's a gasket on the bottom here that seals it to the frame of the motor. So let's start by moving the shorting bars. You know what? The shorting bars were stacked up. They did provide extras, so I am going to use those. Okay, and that's the motor, rewired for low voltage. Bars there, bars across the top. Okay, now the phases come in and connect to these bottom terminals. Actually, you know, they could be the middle terminals too. So the 3 phases are going to connect here, and the ground's going to connect here. Okay, here's the cable that I'm going to use. This is an SE000W cord, so it's flexible. It's got 4 conductors inside, green for ground, plus the 3 phases. And this is going to be oil resistant, flexible, rated up to 600 volts. So this should be a good service cord to use for this application. Now I have to strip the end of it. It's going to be coming in here, and I want to have enough wire to bring the ground around and connect it down on the bottom. So I'll strip about this much of it and see where that leaves us. I'll probably strip it just a little bit longer. Now I'm just very carefully slitting this with a utility knife. And no, this is not the right way to do it. My hope is that by just scoring it, I'll then be able to tear it. So I didn't cut all the way through the insulation because I didn't want to risk cutting into the wires underneath. But I just scored it, and then that's allowing me to peel it. This cable gland has a rubber grip on it, and there's actually a little piece of membrane in there that I had to poke and make a hole with a knife so that the cable could go in. So just run that in, probably to about there. So the cable gland is gripping on the insulation, but we don't have the thick cable inside here that we have to deal with. Now I'll just clamp that down. Now I'm going to use ring terminals, not spade terminals, or not terminals with a fork on the end. I'm actually going to use a ring, and the reason is because I don't want these things to rattle loose. Okay, that's the ground, and I'm going to put the ground on first, just because it's so hard to get to. So I'm going to move the terminal block by loosening this, or taking out this one screw that's holding it down. And that will then allow me access to the ground screw down here. Okay, I've been messing around with this for a few minutes, and I think the best thing to do is just to do it this way. Pull the cover, the frame of the cover back, the box back. Good solid ground connection. Now we can get everything else back on top. Go ahead and put the terminal block back on. Okay, there we go. So we've got the ground on under there. Now we just have to hook these 3 phases to these 3, and I'm going to do this in such a way that they're the same length, because at some point later I may need to swap one of them to get the motor turning the right direction. Okay, that's that. We've got the motor rewired according to the diagram for low voltage, and we've got our phases connected, and I've gone white, black, red. I'll use the same ordering on the VFD for T1, T2, T3, and we'll see if that ends up being correct. If not, all we have to do is swap one wire in order to make the motor rotate in the opposite direction, and we can either do that at this end or we can do it at the VFD end. It doesn't really matter. But that's it for the motor wiring. So let me put the cover on and let's seal it up. Okay. Okay, now we need to hook the other end up to the VFD. Now the VFD has a series of terminals down here on the front. It's actually got 2 rows of terminals. The ones up on the top are low voltage, and those, except for the relay, which could be higher voltage, but these terminals are for external controls and analog input and output. But these are the control circuits of the VFD. There's also a serial connector, so you can hook it up to a bus system to control it. And then the power terminals are down here below. There's 2 ground terminals that are attached to the heatsink, and then you've got L1 and L3, which are the line and neutral. They're on a 3-phase input, there would be 3 input terminals here, but there's only 2 on this one. And then the 3 output phases to go to the motor. So I'm going to go ahead and hook the motor up. This is the other end of the cable that's attached, that we just attached to the motor, and I basically gave it the same treatment. I just stripped it down and crimped terminals on the end. Now I used a ring terminal for the ground because we have an exposed screw to put that under, but for the 3 phases I used forked terminals here because they have to go into the screw lugs on the front, the screw terminal. So let's connect the ground first, and then we loosen all these screws and we'll connect the 3 phases to T1, T2, and T3. Check and make sure those are fully secured. Okay, that's the output. Now for the input power, I have some heavier cable. This is 12 gauge Service Junior, so this is SJ-E00W. So that just means that it's only rated for 300 volts instead of for 600 volts, but that's going to be fine because we're only dealing with 120 on the input. Now this is 12 gauge to handle the additional current, because when this steps up the voltage, it steps down the current as well, meaning to get the 4.3 amps maximum that it could be outputting on the phases, it can pull up to 19 amps if you're running this all the way at the low end of the 100 volt supply. So we'll be using 12 gauge cable for that. I'm not going to wire this up just yet because ultimately when this goes in a box we'll have a contactor. I'm just going to do this temporarily, and I have a line cord that I use for testing that's already got some terminals on the ends, and I'm just going to go ahead and use this. Now this is not heavy enough to handle 19 amps, but it doesn't matter because we're not going to be running any load on this. We're just going to do an initial bench test. So let me hook this up the same way. Ground first. Okay, that's all we should need for an initial test. So let's plug this in, power it on, and see what it'll do. I've got tape on the output shaft here just to make it easy to see on camera if it spins. And so we'll plug it in and see if the blue smoke comes out. Okay, I got zeros flashing on the display. Which is not at all what I expected. I expected it to come up at 5 hertz and to be able to run it. Okay, let me unplug it and grab the manual.